Hello dear students, today we will be studying about polysaccharides and their significances. Polysaccharides are ubiquitous biopolymers built up from few types of hexoses, hexose derivatives and pentoses. They are high molecular weight substances composed of a large number of monosaccharide units to form one large molecule. Polysaccharides commonly found in food are starch, dextrins, glycogen, cellulose, hemicelluloses, pentosanes and pectic substances. The general scientific term for polysaccharides is glycans. Polysaccharides, which consist of one type of sugar structural units, are homoglycans, and if two or several types of sugar units, they are heteroglycans. The monosaccharides may be joined in a linear pattern or in a branched fashion. The number of monosaccharide units in a polysaccharide term its degree of polymerization varies. Only a few polysaccharides have a degree of polymerization less than 100. Most have degree of polymerization in the range 200 to 3000. Their acidic hydrolysis yields monosaccharides. Partial, chemical and enzymatic hydrolysis in addition to total hydrolysis are of importance for structural elucidation. The larger ones like cellulose have a degree of polymerization of 7000 to 15000. The frequency of branching sites and the length of side chains varies. It is estimated that more than 90% of the considerable carbohydrate mass in nature is in the form of polysaccharides and 99% are in plants. Polysaccharides are extremely common in nature and cellulose is the most common organic compound on the planet. Polysaccharides serve plants and animals in three ways: cellulose, hemicelluloses, pentosanes and pectic substances provide structural material. Chitin and mucopolysaccharides serve this purpose in animals. Starch, dextrin and fructan in plants and glycogen in animals provide food reserve. Polysaccharides attract and retain water so that life's enzymic processes are not impeded under dehydrating conditions. Isolated polysaccharides are utilized to a great extent in food processing either in native or in modified forms as thickening or gel setting agents, stabilizers for emulsion and dispersions, film forming, coating substances to protect the sensitive foods from undesired change, and inert fillers to increase the proportion of indigestible ballast substances in a diet. Cellulose. Cellulose is the world's most abundant naturally occurring organic substance, rivaled only by chitin. It has been estimated that nature synthesizes from 100 to 1000 billion metric tons of cellulose every year. It is therefore not surprising that humans have made use of cellulose on a vast scale in the paper, mining, building and allied industries, and as a source of bioenergy. Wood pulp is the main source of processed cellulose, the bulk of which is converted to paper and cardboard, and about 2% amounting to just over 3 million tons into regenerated fiber and films or chemical derivatives. Cellulose is a high molecular weight, linear, insoluble homopolymer of repeating alpha-D glucopyranosyl units joined by 1,4-glycosidic linkage. Because of their linearity and stereoregular nature, cellulose molecules associate over extended regions forming polycrystalline fibrous bundles. Crystalline regions are held together by large number of hydrogen bonds. They are separated by and connected to amorphous regions. Cellulose is insoluble because in order for it to dissolve, most of these hydrogen bonds would have to be released at once. Cellulose can, however, through substitution be converted into water-soluble gums. Cellulose and its modified forms serve as dietary fiber because they do not contribute significant nourishment or calories as they pass through the human digestive system. A purified cellulose powder is available as a food ingredient. High quality cellulose can be obtained from wood through pulping and subsequent purification. Chemical purity is not required for food use because cellulosic cell wall materials are components of all fruits and vegetables and many of their products. The powdered cellulose used in foods has negligible flavor, color and microbial contamination. Powdered cellulose is often added to bread to provide non-caloric bulk. Reduced calorie baked goods made with powdered cellulose not only have an increased content of dietary fiber but also stay moist and fresh longer. Cellulose is a hygroscopic material, insoluble but able to swell in water, dilute acid and most solvents. Solubility can be achieved in concentrated acid but at the expense of considerable degradation through acetyl hydrolysis. Alkali solutions lead to considerable swelling and dissolution of hemicelluloses present. Cellulose is not digested in the human system and acts as roughage or dietary fiber. It can be broken down to glucose by certain microbial enzymes. This is the way cellulose is hydrolyzed in the rumen of animals to provide them with sugar. Some physically modified celluloses are used in food processing units like microfibrillated cellulose. The assay for microfibrillated cellulose is described in the Food Chemicals Codex and involved titration by ferrous ammonium sulfate of a potassium dichromate and sulfuric acid treated solution of the cellulose. MFC has considerably more water retention capability than normal grade materials and is considerably less prone to precipitation in the cuprethylene diamine residue test, Queen test. Microcrystalline cellulose. Microcrystalline cellulose is produced by treating nitrile cellulose with hydrochloric acid and to dissolve the amorphous regions of the polysaccharide, leaving behind the less reactive crystalline region as fine crystal. As with MFC, the viscosity of the dispersion of this product is both pH and heat invariant. A number of varieties are available: powdered, bulk dried colloidal, spray dried colloidal and spray dried with sweet whey. Chemically modified cellulose derivatives. Despite the wide variety of cellulose derivatives that have been made, notably acetate and nitrate esters, only a few of the cellulose ethers find application in foodstuffs. The most widely used cellulose derivatives is sodium CMC. Other ethers have unique and interesting properties, however, which ensure their inclusion in a widening array of products. Thus, for example, methyl cellulose and hydroxyl propyl methyl cellulose find uses as a result of interfacial activity and their ability to form gels on heating. Naturally, individual suppliers have their own technologies, but the production process can be broken down into the generation of alkali cellulose, alkylation or hydroxyalkylation and finally product purification. Applications in foods. Cellulose and its physical and chemical derivatives have long been used in fabricating formulated foods. The physically modified celluloses are useful in many products where bulk properties are desirable. This would include reduced or low calorie foods, flavor oil imbibers or flowable products such as artificial sweeteners and flavor packets. The use of these cellulosics is generally due to their rheology, controlled water interaction and textural attributes, and not to solubility or other chemical properties. Hence, MCC and finely ground cellulose perform a valuable bulking role in calorie foods. 5 important roles for the chemically modified cellulose derivatives in foods are the regulation of rheological properties, emulsification, stabilization of foams, modification of ice crystal formation and growth, and water binding capacity. When a choice is to be made, a number of parameters must be considered. First, the chemical structure of the polymer. Second, the molecular weight of the polymer. Third, the presence of other active ingredients in the food matrix. Fourth, the processing operations to which the food will be subjected. And the last, the physical properties including fiber dimension of the polymer. Starch. Starch unique chemical and physical characteristics and nutritional quality set it apart from all other carbohydrates. Starch is the predominant food reserve substance in plants and provide 70 to 80% of the calories consumed in humans worldwide. Starch and starch hydrolysis products constitute most of the digestible carbohydrate in the human diet. Starch is unique among carbohydrates because it occurs naturally as directly particles. Starch granules are relatively dense and insoluble and hydrate only slightly in cold water. They can be dispersed in water, producing low viscosity slurries that can be easily mixed and pumped even at concentrations of greater than 35%. The viscosity building, that is thickening power of starch, is realized only when a slurry of granule is cooked. Commercial starches are obtained from cereal grain seeds, particularly from corn, waxy amylose corn, wheat and various rices, and from tubers and roots, particularly potato, sweet potato and tapioca. Starches and modified starches have an enormous number of food uses, including adhesive, binding, clouding, dusting, film forming, foam strengthening, anti-stealing, gelling, glazing, moisture retaining, stabilizing, texturizing and thickening applications. A second uniqueness is that most starch granules are composed of a mixture of two polymers, an essentially linear polysaccharide called amylose and a highly branched polysaccharide called amylopectin. Amylose. Amylose is essentially a linear chain of 1,4 linked alpha-D glycopyranosyl units in glycosidic linkage with carbon atom 4 of the next glucose unit. Amylose molecules have molecular weight of about 10 raised power 6. Amylose is not truly soluble in water but forms hydrated micelles. In such micelles, the long chain is twisted into a helical coil. Amylopectin. Amylopectin is a very large, very highly branched molecule with branch point of alpha 1,4 linkages, but in addition the molecule is branched through alpha 1,6 linkages to the extent of 4 to 5%. Molecular weight from 10 raised power 7 to 5 into 10 raised power 8 makes amylopectin molecule among the largest. Amylopectin is present in all the starches, constituting about 75% of most common starches. Some starches consist entirely of amylopectin and are called waxy starches. Waxy corn, the first grain recognized as one in which the starch consists of only of amylopectin is so termed because when the kernel is cut, the new surface appears vitreous or waxy. Uses of starch in food technology. Cereal kernels may be flaked, rolled or puffed to make ready-to-eat products, or they may be milled into flours, which represents an enormous volume usage in breads, pizzas and other baked products. Disruption of the granule is generally the first step in converting the native starch into useful products, and practically all the hundreds of starches that are marketed as such are thus modified or derivatized in some way. The use of modified starch is generally controlled by government regulations, a complex issue in view of the growing emphasis on fat replacers, products less nutritive but with similar taste and mouthfeel to the genuine article. Small starch granules can serve the same purpose, replacing up to 50% of the fat in frozen desserts. Novel pharmaceutical properties of starch derivatives are exemplified by the 3,5-dinitrobenzoate, which finds application in cases of renal failure on account of its ability to sequester creatinine. Pectins. The term pectins usually used in a generic sense to designate those water-soluble galacto-uronoglycan preparations of varying methyl ester contents and degree of neutralization that are capable of forming gels. In all the natural pectins, some of the carboxyl groups are in the methyl ester form. Commercial pectins are galacto-uronoglycans with various contents of methyl ester groups. Native pectins find in the cell walls and intercellular layers of all land plants are more complex molecules that are converted into commercial products during extraction with acid. Commercial pectin is obtained from citrus peel and apple pomace. The compositions and properties of pectins vary with source. The processes used during preparation and subsequent treatments. During extraction with mild acid, some hydrolytic depolymerization and hydrolysis of methyl ester group occurs. Depending on the isolation conditions, the remaining free carboxylic acid groups may be partly or fully neutralized, that is, partly or fully present as sodium, potassium or ammonium carboxylate groups. Typically, they are present in the sodium salt form. Carrageenans. The carrageenans are mixtures of several related galactans having sulfate half ester groups attached to the sugar units. They are extracted from the red seaweeds with a dilute alkaline solution. The sodium salt of a carrageenan is normally produced. Carrageenans are linear chains of D-galactopyranosyl units joined with alternating 1,3-alpha-D and 1,4-alpha-D glycosidic linkages, with most sugar units having 1 or 2 sulfate groups esterified to a hydroxyl group at carbon atom C2 or carbon C6. The principal structure are termed kappa, iota and lambda carrageenans. There are both gel forming and non-gel forming carrageenan fractions. Both form stable complexes with proteins and other gums. They are used in dairy products because They form stabilizing complexes with milk proteins to give a more acceptable texture to processed dairy products. Carrageenan products, of which there may be well more than 100 for different specific applications from a single supplier, contain different proportions of the three main behavioral types: kappa, iota and lambda. Glycogen. This is the storage polysaccharide in animals and hence is sometimes called animal starch. Glycogen is made primarily by the liver and the muscles, but can also be made by glycogenesis within the brain and stomach. Liver glycogen rapidly hydrolyzes to D-glucose after slaughter of animals. Glycogen is a branched chain polysaccharide resembling amylopectin rather than amylose, but is more branched than amylopectin. In the liver hepatocytes, glycogen can compose up to 8% of the fresh weight soon after a meal. Only the glycogen stored in the liver can be made accessible to other organs. In the muscles, glycogen is found in a low concentration of 1 or 2% of the muscle mass. The amount of glycogen stored in the body, especially within the muscle, liver and red blood cells, varies with physical activity, basal metabolic rate and eating habits such as intermittent fasting. Small amounts of glycogen are found in the kidneys and even smaller amount in certain glial cells in the brain and white blood cells. The uterus also stores glycogen during pregnancy to nourish the embryo. Chitin. Chitin is one of the many naturally occurring polymers. It forms a structurally component of many animals such as exoskeleton. Over time, it is biodegradable in the natural environment. Its breakdown may be catalyzed by the enzymes called chitinases, secreted by microorganisms such as bacteria and fungi and produced by some plants. Some of these microorganisms have receptors to simple sugars from the decomposition of chitin. If chitin is detected, then they produce enzyme to digest it by cleaving the glycosidic bonds in order to convert it to simple sugars and ammonia. Chemically, chitin is closely related to chitosan. It is also closely related to cellulose in that it is a long unbranched chain of glucose derivatives. Both materials contribute structure and strength, protecting the organism. Gums. Most gums are polysaccharides. These are incorporated to improve texture, water retention and rehydration of many dehydrated, frozen and instant convenient foods. Gums function as thickeners for gravies and sauces, emulsion stabilizers in salad dressings, foam stabilizers in whipped, popping and beer, clarifying agents for wines and beer, flavor fixing agents and lubricants. The best known plant exudates are gum arabic, caraya and tragacanth. Agar. It is an extract from red and brown algae. It's mainly alpha D and alpha L galactan, where galactose residues are sulfated at various hydroxyl positions. Agar forms the strongest and most stable gels at lowest concentrations. Agar gels are transparent and reversible upon heating and cooling. Therefore, agar finds several uses in stabilizing food products. Curdlan. Curdlan is a bacterial polysaccharide produced by Agrobacterium biovar. It is a 1,3 linked alpha glycan that has a unique property of forming gels when solutions of it are heated. Curdlan forms two types of gels that differ in thermoreversibility. A thermally reversible gel is formed when solutions of curdlan are heated to about 65 degrees centigrade, then cooled to about 60 degrees centigrade. However, when curdlan solutions are heated to about 80 degrees, a strongly thermally irreversible gel forms, that is, a solution is not reformed upon cooling. Gel strength continues to increase with increasing temperature up to about 130 degrees centigrade. Algin. Algin, it is a product of brown algae. It is composed of D-manuronic and D-galacturonic acid. The carboxylic groups are neutralized by various natural cations. If they are replaced by a single cation like sodium, potassium, ammonium, the product is called an alginate. When the cations are removed, insoluble alginic acid are produced. Alginates give widely variable salts and viscosity properties in acid and salt solutions. They form gels and films and find a number of food uses. Dietary fiber. Dietary fiber is defined as the edible parts of plant or analogous carbohydrates that are resistant to digestion and absorption in the human intestines. Dietary fiber is often divided into soluble and insoluble fiber. Gum, mucilage and pectin are soluble fibers, whereas cellulose, lignin, hemicellulose is insoluble fiber. One of the important dietary fiber is beta-glucan. It is a linear chain of alpha D glycopyranosyl units. About 70% are linked by 1,4 and about 30% by 1,3 linkages. Such 1,4-1,3 alpha linkages are often called mixed linkage beta-glucans. When taken orally in foods, beta-glucan reduces postprandial serum glucose level and the insulin response, that is, they moderate the glycemic response in both the normal and diabetic human subjects. They also control blood cholesterol levels, lessen the chance of heart disease and reduce the chances of colonic cancer, probably due to their sweeping action. They increase intestinal and fecal bulk, which lowers the intestinal transit time and helps prevent constipation. Their presence in food induces satiety at mealtime. Nutritionists set requirement of dietary fiber at 25 to 50 grams per day. Kidney and navy beans are especially good sources of dietary fiber. A product based on psyllium seed hulls has high water binding properties, leading to rapid transit time in the gastrointestinal tract and is used to prevent constipation. With this, we conclude today's topic, that is polysaccharides and their significance, and we hope you have understood the topic. Thank you.